Today we start on topics closure of a set. Okay, closure of a set. In previous class we also discussed about closed set and how closed set is important in analysis or in matrix space, and so many important properties supremum of infimum of in this set is belongs to this closed set. Now we're going to this definition of closure of a set. We start from definition. Okay, definition: let X D be a matrix space. Let X D be a matrix space and a subset of X, and a subset of X. Let limit of A denote the set of all limit points of A. Denote the set of all limit points of A. Thus limit of A equal to y belongs to X such that for every r greater than 0, the set PYR intersection A not equal to 5. Okay. Now we denote this one is the limit of A or closure, or we appropriately this one is the closure of A. Okay, so we now prove one exercise about this closure point. Limit of A is the smallest closed set containing A, or A closure is the smallest closed set containing A. Okay, then how we prove it? We prove it so easily. Let X be a limit point of let X be a limit point of A closure. Okay, then there exists a sequence in A closure. Then there exists a sequence in A closure such a sequence xn in A closure such that xn tending to x. Okay, since xn is a limit point of A, since xn is a limit point of A, there exists an belongs to A such that t of xn an less than 1 by n. Okay, for each n, then d of an x less than d of an xn plus d of xn x less than 1 by n plus epsilon for epsilon greater than 0 equal to epsilon as n tending to infinity. Okay, now we show that then an tending to x. Okay, so x is a limit point of A, and then x belongs to A1. So x is a limit point of A. So x is a limit point of A. This implies x belongs to A bar. Okay. Then x belongs to limit point of A bar implies that x belongs to A bar. So A bar is closed. Now we see that this A bar is the smallest closed set. Okay, this A bar is the smallest closed set. How we see? Well, it is above portion. Okay, how we see this A bar is the smallest closed set. Okay, this one, let B be any closed set. Let B be any closed set containing A. Okay. Now if x belongs to A bar, if x belongs to A bar, then there exists a x, then x is a limit point of A. Then x is a limit point of A. Limit point of A. Okay, and hence also of B, and hence also of B. Hence A closure subset of B. If x belongs to A bar, A or A closure, then x is a limit point of A. Okay, x is a limit point of A. This and hence x also of B. That means x is a limit point of B because A subset of B. Okay, A subset of B. Then hence A closure subset of B. So we prove that A closure is the smallest closed set containing A. Okay, now we erase this portion and going to further discussions about this closure. Now we know about that A closure is the smallest closed set containing A, and we also prove this. Now we're going to further then show that in a matrix space BXR closed ball BXR closed ball closure open ball closure subset of BXR closed ball. Okay, now question is that so that in a matrix space this BXR closure equal to BXR closed one. Okay, now how we show it? We show it so simply. First we start about B0R open, this one contained in BXR closed. Okay, BXR closed wall is a closed set. Okay, and also it contains B0R open. Okay, hence B0R closure subset of BXR, and BXR is a closed set and it contains bxr. So its closure bxr closure equal subset of bxr. Okay, how this one possible? Okay, this one possible because if bxr, this means x difference are less than y less than x plus r. Okay, then if its closure means just limit point at it, this one possible or this one possible or either this one possible. Okay, those are the closure of this set. So this one is subset of this. Now we draw one matrix space where bx are closure is a proper subset of bxr. We first choose about that if x equal to any 2-point set AB. Okay, and this one is discrete matrix space. That means bxr equal to singleton A, that var equal to singleton A if r less than 1. Okay, because we know about that dxy equal to 0 if x not equal to, if x equal to y, and 1 if x not equal to y. Then here b, this one b a r. Okay, here r equal to 1 considered, then this one equal to ab, this one equal to x. Okay, so we saw about that var closure equal to this one and b closed ar equal to x. So this one is a proper subset of b closed xr. Okay, so we saw that in discrete matrix space this one is possible. In discrete matrix space this one is possible. Okay, next we going to another example or another problem also similar to this problem. In Rn bx open bxr ball closure equal to closed bxr ball. How we prove it? We prove it so simply. Just we write this question now. In Rn open bxr closure equal to bxr. Okay, how we do this? We do this simple way. We first show that b01 closure equal to b01. Okay, in any non-linear space. In any non-linear space. Since b01 subset of b01 closure, it is enough to show that if u belongs to b01, with if u belongs to B01 closed with norm u equal to 1, then u is a limit point of B01. Now we consider xn equal to tnu, where tn equal to n minus 1 by n. Then xn belongs to B01 and xn tending to u. Okay, so what we get u is a limit point of B01. Okay, xn equal to tnu, xn converts to u, and this one belongs to B closed 01. So we show that u is a limit point of B01. Okay, then our proof is done. That means B01 closure equal to B01. Okay, so we proceed this further. That means B0R closure equal to B0R, and obviously if we shift this origin 0 to x, then xr closure equal to bx. Okay, just shifting this origin. Here we extend radius also r from 1, and here we shifting this origin, then we get this one. Next we give one example. Okay, we're going to one example which also discuss about that. That means how this closure behaves, that in R. Okay, that means q. First we start about q, set of rational numbers. Q closure equal to what? Q closure equal to what? Q closure we take any point x belongs to R, then bx small r, this ball intersection q not equal to 5. Okay, where r greater than 0, then this one is the bx, this one intersection q not equal to 5. So we get this q closure. That means then x is a limit point of, then we show that x is a limit point of x belongs to q closure. Okay, then since x is arbitrary, so q closure equal to r. Next we're going to another questions. This questions is so simple. Z closure equal to how much? we first see that z closure. Okay, let y belongs to, if we state that y belongs to R, then this intersection z is always positive. Not possible, because all time this one is not whole. Okay, then if y belongs to z, then py r intersection z not equal to 5 for r greater than 0. Here y minus r, y plus r intersection z not equal to 5 for r greater than 0. Then this implies y belongs to z closure. So we show that just z closure equal to z. If we had if we take q, then this one is not possible, because if half we consider and 1 3 and half minus 1 3, then this one not contain intersection z equal to 5. If any real number, then this one hold. So we can't consider any number other than z. So z is here, z closure equal to z. Okay, now we're going to further example. Further example we also show now. Minus 1 0 union n closure equal to how much? Okay, then what we learn from here, if we take a belongs to n, then this one is obviously a belongs to n, then bar intersection this minus 1 0 union n not equal to 5. Obviously this one is possible. That means this a belongs to this closure or this limit point. Okay, that means n, all n, a is arbitrary, so all n is done. Now we consider p belongs to any point belonging to 0 1 closure. Okay, b belongs to any point belonging to 0 1 closure, then br intersection this one not equal to, okay, any point, if minus 1 then minus 1 r for r greater than 0. This implies that b belongs to obviously this one. So what we get from here, this one is easy. G minus 1 0 union n closure equal to minus 1 0 union closed union n. Understand? This one is so simply we do it. Next we proceed further example. We erase this problem now. We're going to further example, similar example of open 0 1 union closed 3 4 closure equal to what? Okay, equal to what? How we obtain this? We obtain so simply this one. Let x belongs to 0 1 closed, then this one implies that vx are intersection 0 1 union 3 4 not equal to 5 for r greater than 0. This implies x belongs to this closure. Okay, now obviously we let x belongs to any 3 4 point or y belongs to any 3 4 point. Okay, this implies py r intersection 0 1 union 3 4 not equal to 5 for r. This implies y belongs to 0 1 union 3 4. Hence 0 1 union 3 4 closure equal to 0 1 union 3 4. Okay, now we're going to further discussion about one example of or one relations between this closure of some sets. How this one, that means how this one is related each other. That means A union B closure equal to A closure union B closure. How this one is, we prove it. Okay, and also we prove it if a subset of B, this implies A closure in subset of B closure. Also we prove A intersection B closure subset of A closure intersection B closure. Okay, but converse is not true. So first we prove A subset of B implies A closure subset of B closure. We know about that A subset of B. Now let X belongs to A closure. Then what we get? We get this one implies that Bx are intersection A not equal to 5 for r greater than 0. This implies that Px are intersection B not equal to 5. This implies that X belongs to B closure. So this implies that A closure subset of B closure. For this one hold. Now we're going to further how discuss about this. A subset of A union B, this implies that A closure subset of A union B closure, and B subset of A union B, this implies that B closure subset of A union B closure. So from this two we said about that A union B closure subset of A union B closure. Okay, now we're going to prove of this that means we call proof of this next result. Next result is this one. We have to show that this one A union B closure subset of A closure union B closure. We know about that A closure B closed set, B closure B closed, both are closed, then A closure union B closure B closed. Okay, A closure union B closure B closed, and obviously A union B closure be the smallest closed set containing A and B, containing A union B. This implies that whereas are problems. This implies that A union B closure smallest closed set containing A and B. So what we obtain? We obtain A closure union B closure be a closed set. Okay, but also containing A and B, containing A and B. So this implies that A union B closure subset of A closure union B closure. Okay, so from these two results, this one is the first result. Here we obtain this one mark at 1, this one mark as 2. So from 1 and 2 we get A union B closure equal to A closure union B closure. Okay, next we proceed further. How we discuss about this one is too easy. We know about that A intersection B subset of A intersection B subset of B. This implies that A intersection B closure subset of A closure. This implies that A intersection B closure subset of B closure. This implies that A intersection B closure subset of A closure intersection B closure. Okay. Now we're going to further. That means converse is not hold in intersection. Converse is not hold in intersection. How this one is proved? We take A equal to Q and P equal to R difference Q. Okay. Then what we found? We know about that A closure equal to R and B closure equal to R, and A intersection B equal to phi. So A intersection B closure equal to phi. Then obviously we done it. A intersection B closure subset of A closure intersection B closure. But converse is not hold. So we do this problem easily. Now erase this total problem, and today we stop here.